You know, all around us, these massive, powerful machines are performing these incredible tasks with just pinpoint precision. But have you ever stopped to wonder how? Seriously, behind every single powerful movement, there's this invisible world of mechanical control. It's like a symphony of parts that are designed to transfer, to stop, and to connect power. So today we're going to pull back the curtain on the unsung heroes of all machinery: drives, brakes, and clutches.
I mean, really, think about it. How does something absolutely massive, like an industrial loom, go from a dead stop to full speed and then halt in an instant without just tearing itself to pieces? Well, the magic behind that lies in three distinct but totally interconnected systems. Okay, so first things first. You can't control motion if you can't even create it, right? So the very first problem you've got to solve is how to get that raw power from a motor to the machine itself. And that's the job of the drive system.
Historically, there were two main ways people went about this. On one hand, you had the group drive. Just picture in your head a 19th century factory floor. You've got one enormous motor turning this long overhead shaft, and then all these belts dropping down to power dozens of machines at once. The modern way, though, is the individual drive, and it's pretty much exactly what it sounds like. One motor for one machine. It's a much more, personal relationship between the power and the task.
So why don't we see that old group system anymore? Why is it basically a museum piece? Well, for starters, it was just incredibly inefficient. All those spinning shafts and slipping belts, they just bled power constantly. But the real killer, it was its single point of failure. If that one giant motor broke down, the entire factory went silent. And beyond that, it was just a mess. It created this cluttered, dangerous forest of belts that blocked all the light and made the space nearly impossible to clean, let alone reconfigure.
The individual drive, on the other hand, solved all of these problems. Bam! It's way more efficient with power. It clears up the whole workspace, which makes it safer, brighter, and a lot more flexible. And, if one motor fails, well, only one machine goes down. It's really no wonder it became the modern standard for pretty much everything, from automatic looms all the way to the power tools you have in your own workshop.
Okay, so we've got power to the machine, we're moving, but getting it to stop is just as important, maybe even more so. And that brings us to the world of brakes.
At its absolute core, a brake is really just an energy converter. It doesn't make motion magically disappear. What it does is it takes the energy of that movement, the kinetic energy, and it transforms it into heat, all through friction. Seriously, every time you hit the brakes in your car, you are fundamentally just turning speed into warmth.
And the braking process, it's pretty much always this four-step dance. First, some kind of force is applied, like you stepping on a pedal. Second, that force pushes a friction material, usually called a shoe, up against a moving part, like a rotating drum. Third, friction does its thing, converting all that motion into heat. And finally, with its kinetic energy all drained away, the motion stops. Simple as that.
But here's the catch. The thing engineers really obsess over. All of that heat that gets generated has to go somewhere. I mean, if it builds up too much, the brake can overheat and fail. It's a thing called brake fade. So a huge part of brake design isn't just about stopping power, it's about figuring out how to get rid of all that intense heat effectively.
Now, brakes come in all sorts of shapes and sizes, but let's take a quick look at three classic mechanical designs that are mentioned in our source material here.
First up, we've got the block brake. This is braking in its purest, simplest form. You've got a spinning drum, and a lever presses a block, or a shoe, against the outside of it. It's basically the mechanical equivalent of putting your hand on a spinning bicycle wheel to slow it down. It's simple, it's direct, and it's really powerful.
Next, we have the internal expanding brake. And with this one, all the action happens on the inside. The brake shoes are actually housed within the drum, and when you hit the brakes, they expand outwards, pressing against that inner surface. This design is great because it protects all the braking parts from dirt and water, which is a big reason why it became a classic for cars. And our third type is the band brake. Now, instead of a rigid shoe, this design uses a flexible steel band that's lined with friction material. When the brake gets applied, that band wraps and tightens right around the drum, gripping it like a vise to bring the whole thing to a halt. It's an incredibly effective design that you'll find on heavy machinery, like industrial warpers.
All right, so we can start motion with a drive, and we can stop it with a brake. But what if you need to, say, temporarily disconnect the motor from the machine without shutting everything down? For that, you need our third component, the clutch. You should think of it less like a brake and more like a mechanical on-off switch for power.
You know, this quote from our source text just sums it up perfectly. The clutch sits right there in the middle, Between the power source, the motor, and the thing doing the work, the machine. It's the mediator. It's the one controlling whether or not power gets to flow across that gap.
So, why is this so important? Well, because starting a heavy machine from a dead stop puts this enormous, sudden strain on a motor. Trying to do that could literally burn out its coils. A clutch solves this problem by allowing the motor to spin up freely, get to its happy place at optimal speed, and then gently engage to transfer that power over to the machine. It's an absolutely essential safeguard.
Now, generally speaking, clutches connect power in one of two ways. You have your positive lockup clutches, which are basically like a light switch. They are either fully on or fully off. There is no in-between. And then you have friction clutches, which are way more like a dimmer switch, allowing for a really smooth, gradual connection.
A perfect example of that light switch style is the jaw clutch. It's got these two discs with teeth, or jaws, that literally mesh together. When they engage, boom, it forms a solid, rigid connection. There's no slip, no gray area. The power is either flowing or it isn't.
And for the dimmer switch style, a great example is the common single-plate clutch. With this one, a spinning plate from the motor is brought into contact with a stationary plate that's connected to the machine. Springs press them together, and the friction between them gradually brings the machine's plate up to the same speed as the motor. This is what allows for that smooth, controlled engagement we were talking about.
So, let's bring it all home. It's actually pretty simple when you boil it down. Drives are for moving power, brakes are for stopping power by turning motion into heat, and clutches, they're for interrupting power, acting as that crucial switch to protect the motor and control how that power connects. 3 different jobs, but all working toward one goal: precise control over motion.
So next time you see a machine in action, any machine at all, look a little closer. Try and picture that invisible dance that's happening inside, that intricate interplay of the drive, the brake, and the clutch. That really makes our entire mechanical world possible.